associated to it, those kind of graphs are called directed graphs. Simple. Okay. So in graph theory, understanding the terms will take time, but once you understand these terminologies, graph theory will be little bit easier to you. And also very simple. If you learn it, you can grasp the concept within very short time. So this is called directed graph, the graph in which each some edges have directions associated to it. So now tell me, what will be the undirected graph? Anyone?
In which direction are not associated?
In which
Direction is not specific.
At least one edge is not directed.
no, it's not at least. So if all the edges don't have any direction associated to it,
Okay.
then they are called undirected graphs. So you see in this example itself, if it is like this, even though if you have one directed edge, that particular graph is called directed graph. So you have this one edge which has direction. Even I will remove direction to this also. Okay. So even though if you have one edge which has direction, that particular graph is called directed graph. So the undirected graph will be like, if all the edges do not have any direction, or having no direction means it is saying that it is bidirectional. So note this point. So no direction to edge, or all the edges are bidirectional. Meaning like this. So if I have this edge is bidirectional like this. So this edge is called as bidirectional if it goes in both the directions, B, and bidirectional to C, and bidirectional to D, and bidirection to A. So now you see direction will not play any role here. So that edge can go to and fro. So there is no requirement of direction to show. So simply we will remove the direction, and undirected graph, the edge in an undirected graph represents both the bidirection thing. So you can either go from A to B via this edge, or you can come from B to A. Both works for an undirected graph. So simply no direction in our graph theory, no direction to the edge is same as saying all the edges are bidirectional. Okay. Any doubt here?
No,
Any
sir.
doubt in directed, undirected? Yeah. Okay, let's move a little forward and see different types of graphs we have. So this is just the types in regards to the directedness and undirectedness of edges. So these are the two different types. But there are many other types like cyclic graph, so which I am not going to cover, but I am giving you. You can just go through this. What are these graphs mean? So there are some types called cyclic graphs, and there is acyclic graphs. There is connected graphs. So there are many. So each one of it has a different definition, and if a graph satisfies that definition, it will fall into that class. So connected, disconnected. Complete graph. So I will explain what is complete graph. So complete graph, planar graph. So like this graphs. Then there is trees. So trees also I will cover. But if you are interested, you just go and look at. So acyclic also, when we deal directed acyclic graphs, There I will mention, I will say what is cyclic and acyclic is. And connected, disconnected, if you are interested, you just go and watch the lectures. And complete graph also I will cover. Planar also the same thing. In the lectures it is given. So if I start explaining these things, I may not cover all the topics. So that is why I am skipping few. So let us see few things. Okay, let me start with, anyway we require directed acyclic graphs. I will start with acyclic graph. So let us look what is acyclic graph means. So if a graph, this is the definition, if a graph that does not contain any cycles. So now there is a new term called cycles. So what do we mean by cycles? So let us define that also. So what is cycle? So a cycle is, this is how it is defined. When you start from a vertex, start from any vertex, from a vertex, if I start from a vertex u, let me say it is u in a graph, if you can able to reach back to vertex u by traveling along some edges and vertices, so if you can able to reach back to vertex u by traveling along some edges and vertices, then that is called a cycle. Then the path is called cycle. So this is how the example will be. I will show the example for cycle, you will understand. So there is vertex a, vertex b, vertex c, vertex d and vertex e, and this is how your edges are. So from a to b, b to c, a to c, b to d, d to a, d to e, d to c. So this is how we have the graph. So this graph is a directed graph, as well as it has some 5 vertices with some 1 2 3 4 5 6 7 edges. So now having a cycle means, if you see here, I start at a, so I am at a now, I travel along this edge and reach b, okay, and from b I can travel to d along this edge, and from d I can come back to vertex a. So by starting from vertex a, I have traveled along some edges and vertices, and I can come back to vertex a. So if I can do that, this particular path, so this is the path a to b, b to d and d to a. So this is a path. So path is actually series of vertices along with edges. So this is how the path. So this particular path is called a cycle. So now you got a cycle. So triangle. The cycle is like a triangle. So a to b, b to d, d to a. So this forms a cycle. So if these kind of cycles are there, then that particular graph is called a cyclic graph. If you don't have any cycles in your graph, then those graphs are called acyclic graphs. So you have to check for every point. See, if you start from B, again B to D, D to A to B is a cycle. But B to D, D to E is not a cycle. So if you go to E, you cannot come back to B. Similarly, if I go to C, C is the dead end point. If you reach C, you cannot travel to any other place. So these are not cycles, but at least I got one cycle like this, A to B, B to D, D to A. So this is a cycle. So if you got one cycle in your graph, then that fails the property of acyclicness and it will not be a cyclic graph. Okay.
Hello, sir.
Hope this is clear.
What about A to A?
A to
A. I mean to say, if there is an edge from the same vertex to the same vertex, will it still?
so those kind of edges are called loops, and we are not going to look into those kind of loops.
Okay.
So we are looking only at simple graphs.
Okay.
Okay, simple means there is no loop. So there is no edge that connects the same vertex.
Okay.
Okay, so we are not going to deal those kind of graphs at all in this
Okay.
particular course. Okay.
Okay. Okay.
Yeah. So these graphs are
Hello,
called
sir.
simple graphs. Okay. So that is about acyclic graph means. So cyclic, acyclic. If you find a cycle, that turns out to be a cyclic graph. If you don't find any cycle in your graph, then that graphs are called acyclic graphs. And we will see the importance of this acyclic graphs when we deal this directed acyclic graph. So by now you should be able to connect what is directed acyclic graph means. So it's like it is acyclic as well as it is directed graph. That's it. But in detail we will see. So let us go one by one. Now let us discuss this complete graph. So complete graph is also, so from the name itself you can see complete. So complete means you have to complete, that means you have to add edge between any pair of vertices, every pair of vertices. So you have two vertices, then connect it with direct edge. So you have to complete the graph. So that means formally, if every pair of vertices are connected by an edge, then it is called a complete graph. Okay, for example, so let us take start with 3 vertices, and I will show 4 vertices also. So for 3 vertices, you see, you pick any pair of vertices, an edge is there. Those two pair of vertices are connected by an edge. So this is a complete graph of 3 vertices. Similarly, if I take 4 vertices, 1, 2, 3, 4. So every pair need to be connected by an edge. So 1 and 2 will be connected, 1 and 3 will be connected, 1 and 4 will be connected. Similarly, 2 and 4, 2 and 3, 2 and 1. Already 3 is connected with 1 and 2, so you have to connect 3, 4. So this is a complete graph with 4 vertices. So can you tell me how many number of edges are there in? So when n is 3, so number of vertices are 3. How many number of edges are there?
4.
In my complete graph, in my complete graph,
6. 3.
3. Okay, number of edges are 3. Number of edges are 3. Here, when n is 4, so the number of vertices is 4. Here, how many number of edges are there? 6. Correct. So 1, 2, 3, 4, 5, and 6. And I will just draw 5 also. You tell me how many number of edges will be there in a complete graph of 5 vertices. 10. Correct. Okay. So in this star, you will have 5 edges and the outer edges will be 5. So this is a complete graph of 5 vertices. When n is 5, you will have number of edges as 10. So in general, so this 3, 4, 5, in general, if you have, so if n is, if you have n vertices, if n vertices are there in a complete graph, then the number of edges in that graph will be, anyone?
n into
So
n
for
minus
3 it is 3, for 4 it is 6, for 5 it is 10.
For 6 it's 15, sir.
Yeah. Okay, let me give you NC2. If
n
you
Minus
know,
into
1
n
by
minus
2.
1.
yes. So n into n minus 1 by 2. Okay, choosing 2 vertices out of n vertices. So you have to choose 2 vertices and connect by an edge. So the number of edges will be number of picking 2 pairs from n pairs, n vertices. So that will be NC2, which is n into n minus 1 by 2. So this will work. Okay. So that is about complete graph. Let's look at reachability now. Okay, let's go and see what is this reachability, and then we will look at vertex coloring. Okay, and the other types of planar graphs, connected graphs, you just go and look at the definitions, and the definitions will also be very easy. So right now, whatever the definitions you are seeing, that is how it will be. So connected means no vertex is left isolated, or there is no breakage in the graph, breaks in the graph, like this. Very easy definitions, you can get it. And the next is reachability. So you can see the words itself will give you, the term will itself give you reachability. So is the vertex has the ability to reach to another vertex, is what reachability means. So in our graph theory, reachability refers to, so you find a path to reach from one vertex to another vertex. So if you can able to find the path, then that particular vertex is reachable to the other vertex. So let me write it down. So reachability refers to find a path from one vertex u to another vertex v. So if you find a path, so let me rephrase this. So reachability means if you have a path. So if we have a path from one vertex u to another vertex v, then we say vertex u is reachable, sorry, vertex v is reachable from vertex u. Simply it says that if you are at u, if there is a path, you can travel to v. So treat it like you are at home and you have to go to some place somewhere in Bombay. So if you find a path like I have to take bus from here, I have to go to some place, and from that place I have to take the cab. So if you can able to sketch the path, then you will definitely can reach that particular place. So that is how it is. Reachability means the same thing. So but this is in the graphs within the vertices. So let us take an example for better understanding. So let me take some example here. Suppose let's say there is a directed graph given like this. So vertex A to B, and let me take C here, C, and no direction here, or I will give the bidirection to this, D, and E. I will come back here to B, yep. G. Okay, let me say this is the graph G, and I will use F, and this is a bidirection. Okay, so let's say this is how the graph is, and I can ask you a few questions like, is F reachable from D? So if this is the question, how you have to attempt this? You have to start from D and try to find a path that reaches to F. So if there is a path, then you say yes, F is reachable from D, or you say no, F is not reachable from D. That is how it will be. So let us start. Is F is reachable from D? So now you are at D. You have to go to F here. This is the final point. So can I go? So from D, I cannot go to E, but from D, I can go to C via this edge. And from C, I can go to A. And from A, I can go to B. And from B, yes, there is a edge going to F. And I can reach my destination point F. So the answer will be yes. So yes, is F reachable from D? Yes. Is D reachable from F?
No.
Can anyone answer
No.
this particular
No.
question? No. Why?
No.
Mm.
So now you
F to B,
We
there
can
are
come
no
from F
edge.
to B, but we cannot go from anywhere from B.
from B, right? So B is like end point to it. There is no outward going edges. Okay, from B. So therefore, I cannot reach. Uh, therefore, I can say that D is not reachable from F. So if this is the question, this is how we can answer. What if the question is like this? So what if? Let me ask you. Yeah, find all the vertices that are reachable from, let me give you from C. So what you have to do is, in this question, you have to find all the vertices that are reachable from vertex C, from C. So now you are at C. Right now you are not looking at one reachability, one vertex reachability. Instead you are looking at where all can I go. So if I am at C, where all other vertices I can reach. So what will be the answer?
4
A,
vertices.
B, F, D.
A, B, F, D. Correct, except E. So you see, if I am at C, I can go to D, I can reach D. So vertex D is reachable from C. Again, from this edge, I can reach A. So I can reach A also. Vertex A is reachable. And from here A to I can go to B, and from B I can reach F. So if I am at C, I can reach A, B, F, and D. So like this. Okay, this is also okay, cool. What about this question? So from which, okay, find the vertex from which every other vertex is reachable. So now you have to find a vertex such that from that vertex every other vertex is reachable. What vertex will it be?
C.
So that would be
E.
C or E?
C.
E.
E for elephant.
E, sir.
Yeah. Yeah. E. Correct. So we have asked the question that, so where you have to be such that you can travel to every other vertex. You can actually travel to every other vertex, or you can actually reach to every other vertex. So if I start from C, we have seen already. So from C, I can only reach to A, B, F, D, but I cannot reach E. But for A, you can only reach to B and F. For B, you can only reach to F. And for F, you can only reach to B. And for D, if you see for D, you can reach to C, A, B, F. Again, E is missing. And but for E, if you see for E, if you are at E, you can reach to D, you can reach to C, you can reach to A, you can reach to B via two paths. You can actually travel like this, or directly you can reach to B. And once you reach B, you can also reach F. So every other vertex can be reachable from E. So these are some straightforward questions, right? So if a graph is given to us, within the graph, it is very straightforward. You know the vertices, you know the edges, everything is given, and you can answer it clearly. But let me add some real life scenario to this. Okay, so let me give some real life example. Suppose there are some cities in India. Okay, let us name them also. As we have used, let us name them. Suppose there are some cities in India. Let me start with Delhi, Mumbai, Chennai, Hyderabad, maybe Bangalore, and Kolkata. Okay, there are some 6 cities we have picked, and each of the city has an airport. Okay, and now let us define that there are some cities which has a direct flight, and some cities doesn't have a direct flight. And a graph representing this particular data is shown. Okay, so what we shown is we will draw a graph now. So let me denote it. So Delhi, I will represent it with D, M, C, H, B, and K. Okay. So what we do is we will represent it like this. And what we do is next thing is we will add. If there is a direct flight from Delhi to Mumbai, then there will be an edge connecting, directed edge connecting D and M. So let's suppose say I said okay, before graph I will give, let me give you, so what all cities have direct flights and everything. Let's suppose say from Delhi you have direct flights to Mumbai and Hyderabad. Okay, and from Mumbai, you have direct flights to Chennai, Bangalore, Hyderabad. Okay, and from Chennai, you have a direct flights to Kolkata, and Delhi and Bangalore. Like this, some data will be given to us. So this is the data given to us, and from Hyderabad, there is only one directed flight. Let's say Kolkata to Kolkata, or okay, let's take it Delhi. Okay, and from Bangalore, we have directed flights to Mumbai, Chennai. No, not Chennai, Kolkata. And finally, Kolkata don't have any direct flights to any of the city. Okay, so now this is how the data is given to us. Now we have to draw a graph that represents this data. So how we can draw is by treating these cities as the vertices, and I will give a direct edge from one vertex to other vertex if there is a direct flight connecting to it. So let us draw the graph now. So Delhi is attached to, so from Delhi we have a direct flight to Mumbai and to Hyderabad, and from Mumbai we have direct flights to Chennai, Bangalore and Hyderabad, and from Chennai we have direct flights to Kolkata, to Delhi and to Bangalore. And from Hyderabad we have direct flight to Delhi. So we can give the bidirection to this edge itself. So it's like from Delhi to Hyderabad there is a direct flight, and from Hyderabad to Delhi also there is a direct flight. And from Bangalore we have a direct flight to Mumbai and a flight to Kolkata. That's it. So this is how the graph will be for the given data. So now the questions will be like this. So is there a way to reach from Delhi to Mumbai or Delhi to Bangalore? So is there a way to reach Delhi to Bangalore, or is there a way to reach Delhi to Kolkata? So if you are at Delhi, can you reach Kolkata via these airlines?
Yes, we
Yes,
can.
sir.
Yes, right. From Delhi, you have to travel to Mumbai. From Mumbai, you can catch a flight to Chennai, and from Chennai, you can reach Kolkata. So yes, so from Delhi, I can reach to Kolkata. Or now, if you are at some city, let's say Mumbai. So if you are at Mumbai, which all cities you can reach directly or indirectly also? Which all cities you can reach? So what all cities you can reach if you are at Mumbai?
Mm,
All
Chennai,
cities.
Hyderabad.
All cities, right? So you can travel to Chennai, from Chennai to Delhi, and you can directly travel to Hyderabad, you can directly travel to Bombay, and from Chennai you can travel to Kolkata. So if you are at Mumbai, you can actually travel to all other cities. And yeah, the final question also satisfies Mumbai, I guess. From which city I can actually reach to every other city. So like this. So Mumbai, again Chennai. So Chennai will also answer, will be the answer, I guess. So what else will be? So Mumbai, if you are at Mumbai, you can reach to every other city. So from Chennai also you can reach to every other city.
Hyderabad.
So if you are at Hyderabad, you can reach to Delhi. From Delhi, you can reach to Mumbai. So if you can reach to Mumbai, So that means from Mumbai you can reach to every other city again. Okay, Hyderabad will be the thing. Even from Bangalore, I guess.
Okay.
Yeah. So therefore, except Kolkata, you can reach to all other vertices. If you are at any other place, you can reach to every other place. So this is how we can ask the questions. If a data is involved, if a real life scenario is involved, question looks bit tricky, but if you convert it into graph terms, so you should understand which particular data to be considered as vertex and what data to be converted to the edge. How should I define my edge? So if you are good at these things, then the problem will be very simple. Okay. So here there are only 6 cities. So from the data itself, I can actually say by looking at the data itself, I can actually say. But in India, there are the cities which are having airports are more than some 500 or 1000 cities, right? So there are, so out of those 1000 cities, if I have to connect, if I have to look at the data in the Excel sheet, so if I wanted to find the reachability, that will be very, very difficult. Not difficult, that will be little complex. But if you convert that particular whole data into the graph, you can actually find paths between two nodes and directly say whether it is reachable or not. So that is the advantage of this particular uh, topic in graph theory. So this is where this is useful. Okay. So understood about the reachability. What do we mean by reachability in a graph? Yes, no?
Yes.
No.
Yes.
Oh, okay. Let's see vertex coloring. We will see vertex coloring. So what is this vertex coloring? So vertex coloring or simply coloring or graph coloring. So all are same. So we can say vertex coloring or simply coloring or graph coloring. All these are same. If there is an edge coloring, we will specifically mention that edge coloring. Edge will be mentioned if it is referring to edge coloring. Or else if it is simply we are saying coloring means it will always, we are always saying that vertex coloring. Okay. So what is this vertex coloring? So even this is also very simple. It is to find. So you have to find, vertex coloring means you have to find the minimum number of colors, minimum number of colors required to color all the vertices of a particular graph, See, this is the condition. So you have to find the minimum number of colors required to color all the vertices of the graph, but the condition is such that no two adjacent vertices have the same color. So adjacent means vertices,
Nearby.
yeah, sharing a common edge. Okay. So adjacent means we will take an example and let me give you clarity about adjacency, adjacent vertices, and then we will find the vertex coloring of that graph also. Let us take like this, pick circles properly. Okay. So this is A, from A. This is B. Let it pick C, D, E, E, and yeah, here we will pick A, B, C, D, E, F. Okay. Okay, let's say this is how the graph is. Let me take one more vertex also. A, B, C, D, F, G. So this G is connected to C, D, and E. Okay, this is a graph with 7 vertices and some edges. So edges and vertices means like this. A and B is sharing a common edge. So this is the common edge between A and B. So A, B are adjacent to each other. Similarly, A is adjacent to C because they are sharing a common edge, directed. Similarly, A is adjacent to D. So even they are sharing a common edge. So like this, C is adjacent to A, B, G. Like this. So B is adjacent to what all vertices? So vertex B is adjacent to how many
A,
vertices?
F,
A,
D, E.
C, D, E, F.
A, C, D.
Yes, A, C, D, E, F.
F.
Okay. So this is about adjacent vertices means. So if they share a common edge, then they are called adjacent vertices. Now read the definition. So what we have to do, we have to find the minimum number of colors. So we have to color vertices here. So each vertex to be colored, and what we have to find, the minimum number of colors we have to use to color this all vertices such that no two adjacent vertices have the same color. So if you are giving red color to vertex A, so let us suppose say I have given red color to vertex A. So color 1 or red color, you can choose anything, color 1. So you don't have this coloring in actually, so while you are solving question paper, so say that it is color 1. So denote it as color 1. So if you have given color 1 or the red color to vertex A, so the adjacent vertices, which are adjacent to A should not have the red color. So that means C, D, B shouldn't take red color. So what I will do is I will fill the red color to maximum number of vertices possible. So I will try to fill maximum number of vertices. So if I give it to F, so I can give it to F, right? F is not adjacent to A. I can give it to F. Now once I give it to F, now E cannot take red color. So C cannot take red color, B cannot take red color, E cannot take red color, D cannot take red color,
G can
G
take.
can take
G
red
can
color. So you can fill red color or the color 1 to 3 vertices. So now you are done. So you can't give color 1 to any of the left vertices. So now we have to choose color 2. So you choose the second color, which is blue, let's say blue. Okay. So what you do is you color. So we will color C with blue. Once you color C with blue, you cannot color B
D,
with blue. That's it. You can color D or E with blue.
D,
So whichever. So you can pick this. Okay. Now I am done. So I cannot give blue color also to E and B. I cannot give red. I cannot give blue. So now I have to go to color 3. So which is green. So once I pick green color to vertex B, Can I give green color to vertex E?
No.
No.
No, right? So I have to choose color 4, which is black. Okay. So the minimum number of colors required to color this particular graph is 4.
4.
So the vertex coloring of this graph will be 4.
Can
Okay.
this be
One
mathematically
question.
obtained by, say, number of edges or the vertex with the most number of adjacent vertex, something like that?
No. That comes while you do vertex covering.
Okay.
For vertex covering, we will pick the vertex which is incident with most number of edges. For coloring, it doesn't matter that much. So wherever you start, your adjacent vertex should not contain the same color. So the
I mean to say,
coloring might change. So you might give color 1 to B, G, something like that. But anyway, at last you will be left by choosing 4 colors.
okay, so any order will end up with 4 only.
Yeah, you will end up
Okay.
with 4. But your coloring might change. Maybe B and G you can give the same color,
Okay.
right? So you can give same color to B and G, but A color will be affected.
Okay.
Yeah. Okay. That is how it is. So the coloring is simply like it's a game, puzzle kind of thing. So if a graph is given to us, we have to find minimum number of colors that need to be used in order to color all the vertices. Okay. So that is vertex coloring. You practice, you take few examples. So you can create your own graphs. So I just randomly drew this graph. You can also take some random graphs and try solving for vertex color.
So Srikant, from wherever or whichever vertex we start, it doesn't matter, right?
It doesn't matter. Okay, in this it doesn't matter, but in vertex covering, the later topics, it matters. Okay, we will discuss those things. But for graph coloring or the vertex coloring, it doesn't matter much. 99% of the cases, it doesn't matter. So you can freely pick. Okay. Any doubts?
That's fine.
Okay. So do I have to do one more example on this coloring or let's move ahead?
It's fine. Let us move ahead.
Okay, yeah. Okay, let's move to another concept which is matching. So we will see matching. Okay, before that we will see vertex covering also. Vertex cover also. Okay. So let's see what is this vertex cover means. So vertex cover is the set of, so some subset of vertex set. What you have to do is you have to pick a subset of vertex set V. So subset of the vertex set.
Sorry to interrupt. I tried color 2 with B. I think that we can end with 3 colors. Maybe I'm wrong.
Which color you have taken?
Instead of taking C blue, I've taken B.
Instead of taking C as blue, you have taken. How can you take a blue to B? Because D is taking blue, right?
No. The order, instead of taking C as the second color,
Okay, so you have
I
taken
took
blue
it.
to B, then G takes blue.
Right. Yeah. Sorry, I missed an edge. My mistake. Sorry to disturb.
Okay.
Please go
Yeah,
ahead. Yeah.
yeah. So vertex cover is actually you have to pick a subset of vertex set. Let's say the subset is say VC such that every edge is covered. So I will again define this. What is this covered meaning means? What is this covered meaning means? So for every edge, there will be two vertices incident to it. So see, if this is the edge in a graph, then the left end of the edge will be connected to one vertex and the right end will be connected to another vertex. So let's say I and J. So this is an edge between I and J. So I say this edge is covered if at least one of the I or J is in my vertex cover. So that means if I take I, J intersected with this vertex cover, this should not be equal to 5. 5 means empty set. So that means at least in my vertex cover, I should have I or I should have J. Even if you have both, it's fine. But it shouldn't be like both are not there in my vertex cover. So if both are not there in this vertex cover, then this edge is not covered. So if this edge is not covered, then this particular VC is not the vertex cover. So vertex cover is actually finding the subset of the vertex set such that that subset intersected with any edge vertices, it should not be equal to 5. So we will take an example and we will understand this better. Okay, so let us take this example, some big example. C, D, E, okay, let's take this graph. Now this is the graph and I have to find, so first of all write the vertex set. So the vertex set is A, B, C, D, E, F, G. So there are 7 vertices. Now out of these 7 vertices, I have to choose the subset of it. Let me add minimum also, and we will be looking at minimum vertex cover. So I need the as minimum vertices as possible such that I will cover all the edges. So that is the optimal case for vertex cover. So minimum vertex cover, we will be looking at minimum vertex cover because you see this particular vertex set will be the vertex cover. If you take all the vertices, then that will cover all the edges. So then there is no point of talking about vertex cover itself. So vertex cover means you should cover all the edges. But in this particular topic itself, we will be more focusing on finding the minimum vertex cover. That means I have to choose minimum number of vertices such that every edge is covered. So let us say I will start building this vertex cover. So I will build this slowly. So what I will do is, in order to cover all the edges, what I will do is I will pick the vertex which is incident to most number of edges. So which one is the vertex that is incident to most number of edges?
F.
F.
F or D.
Correct.
F.
F. So I will add this vertex F into my vertex cover. So once if I add F, this edge FD is covered. So at least one of the endpoints of edge should be there. So this F is there, so this edge is covered. This edge is covered. This edge is covered. and this edge is covered. So I covered 4 edges by taking only one vertex. And next, choose the vertex. Now remove these 4 edges and look for the vertex which covers most number of edges. So which vertex will it be? A.
A.
Right. So I will pick A. So once I pick A, this edge is covered, edge AD is covered, edge AB is covered. Now again the same process you follow. So pick the, now remove all the red edges and look in the graph and pick the vertex which covers most number of edges.
E.
E. Right. So add E to your vertex cover. So by adding that, you are covering E and B also. And finally, you are yet to cover this particular edge DG. So you pick any vertex, it's fine. So you have to cover this edge, so you can pick D or G. Both works. So I pick D. So once I pick D, I will cover this particular edge also. So this is what covering means. So once you are taking one vertex, that means you are covering the incident edges. And every edge need to be covered. So this is a vertex cover. This is also a vertex cover. This vertex set is also a vertex cover, but this is the minimum vertex cover. So we have used only 4 vertices. I will show you one more vertex cover where you might go wrong. So I will start with D. Okay. So I will start with D and cover this, this and this. Okay. And I will pick A and I will cover this, this, and I will pick C. I will cover this. Okay. Still I am at to cover this EF edge, EB edge, BF and FG. So I will pick E. Once I pick E, I will cover this and this. And still I have to cover BF and FG and I can pick F. So you see this is also a vertex cover. So this D, A, C, E, F is also a vertex cover. But if you observe clearly, this particular vertex cover has 5 elements inside it. And this is not the minimum vertex cover. But even though it covers all the edges, but this is not the minimum. So you have to find the minimum vertex cover, not the vertex cover. So you can get multiple vertex covers, but among them, you have to find the minimum vertex cover. So you have to use minimum number of vertices and cover all the edges. So that will be the optimal case for this vertex cover. Okay. Any doubts, or do you need one more example? Will you try, or let's move?
Yeah, what is the practical use of this?
Yeah, there are quite a bit practical uses of this. So let me give you a few.
Like
So if we
deciding the junctions where we have to have facilities in railway stations.
that is one thing, or treat this as the streets and CC cameras to be fixed, so that
Oh.
minimum number of CC cameras to be fixed,
Okay.
so that every edge is, every street is being covered. Okay, you understood, right? You have to use minimum number of cameras. So you fix camera here so that this observes this particular street, this particular street and this particular street.
Yeah.
Like that, security systems, or maybe some meeting points. So like this. Okay, so these are the places. These are places. Let's say these are some buildings in a colony. There are some 7 buildings. and each one of you can at most travel one road to the nearest building. Okay, so in these cases also you can use this
Maybe
vertex cover.
internet network or another
Network. So there are lots of things. You can search it online. You can just say real life examples of vertex covering. So there are many, but right now I can recall these things. So yeah, that's about vertex coloring. And you just go through maximum independent set also. I don't want to cover it now, but that is also one interesting topic you might get in graph theory. So maximum independent set, vertex coloring, and next is we will look at into matching. So till now we have dealt with only vertex point of view. So we are trying to pick some subsets of vertex or coloring the vertex. So we will do those things in vertex covering or vertex coloring. But this matching is mainly dependent on the number of edges or the edges. So edges will play a role now. So what is this matching means is you have to pick a subset of edges now. So subset of edge set E, say let's say M. So as this is matching, we say just represent it as M, such that, so this is the condition will be like this, such that no two edges you picked, no two edges that picked have a common vertex. So I will also explain what is this having a common vertex means is also. Then we will look at, then you will understand what is this matching definition. So let me take the same example. So let's bring it down. Okay, let me redraw it. So A, B, C, D, E, F and G. Okay, so this is the graph. So edges having common vertex means, so you see this AB edge and you see this BG edge. So these two edges are having a common vertex which is B. So vertex AB, edge AB and edge BG have a common vertex which is vertex B. So these two edges have a common vertex. So what you have to do is, so these are so you shouldn't pick these two edges in your subset. So if you have picked AB, then you are not allowed to pick BG, BF or AC also. AC also have a common vertex which is A. AC and AB have a common vertex A, and also AE and AB also have a common vertex A. So once if you are picking this, you are not allowed to pick this, this, this and this. Okay, like this I have to pick edges such that all the vertices are also covered. Okay,
Will that be a unique one, or there can be more than
no,
one?
that can have multiple also. Here also
Okay.
that can have multiple.
Okay.
But we will be trying to find. So okay, there is one more condition attached to this, such that no two edges that are picked have a common vertex, and all the vertices. Okay, not all the vertices are covered. No need of these things. So node 2, you have to pick a subset such that no two edges that are picked have a common vertex. Okay, so this is covered. This, if I pick this, I cannot pick, so I have to pick this. Okay, yeah, and I will try to pick maximum number of elements in my subset. I will try to pick the maximum. Okay, I will get the maximum. Pick a maximum subset. Maximum subset of edge set E such that no two edges that are picked have a common vertex. So similarly, the same approach you can follow. So before starting, what you have to do is you pick the edge that is leastly connected to other edges. That is how you have to pick. So I will repeat. So while you find the matchings, you have to pick the edge that are very much leastly connected to other edges. So maybe you have to pick an edge like AC, yeah, like edge AC. So AC is connected to only 3, and similarly you can pick CD also, CD, AC, or BG. So BG is the best pick. BG is also you can pick. So you can pick the edge which is leastly connected. So I have picked the AB that ruled out 4 other edges. But if I had picked BG, that would have ruled out only 3 edges. And I would have got better maximum subset of edge set. So we can try it. So I will pick BG. So my edge set. So my M, I have to build. I pick BG, edge BG. So once I pick edge BG, I'm not allowed to pick this, and this. So once this is done, again I will pick the least edge that is leastly connected. So I can pick AC. So once I pick AC, I'm not allowed to pick
CD
this and this. And then I can pick only one. So I can pick DEF or DE or EF. So AC, DF. So this will be the maximum matching. And if you observe clearly, each edge picks 2 vertices at one point. So if I have chosen BG edge, it has picked vertex B as well as vertex G. So now my other edge shouldn't contain B and G. So those 2 vertices are ruled out. So like this, each edge will take out 2 vertices from the graph. So this edge is taking out these 2 vertices. This edge is taking out these 2 vertices. So you will get vertices in pairs by this. Okay. So a practical example for this kind of matchings is the marriages or classroom mappings. So teacher and classroom. So one teacher should be allotted to one classroom, and there can be multiple classrooms, like 10 classrooms, and each teacher can go into any classroom and she can take. But once if one classroom is taken by one teacher, no other teacher are allowed into that particular classroom. So that particular teacher is fixed to that particular class. So like this. So you can have matching between teacher and the classroom. So once these two are matched, you cannot involve those two things into your graph again, into your headset again. So the remaining teachers will occupy the remaining classrooms. So each teacher will be matched with one particular classroom. like this. So one vertex is matched to other vertex. So yeah, if I can draw, I can show you. So there are A, B, C, D, E. So 5 classrooms, and there are teachers like T1, T2, T3, T4, and T5. So this T1 can go into A, B, C, D, E. So T2 can also go into A, B, C, D, E, like that. So the graph will be like this. So like this. And this will also be every right side vertex will be connected to every left side vertex. So this will be very complicated. The number of edges will be very more. So it will be like 5 factorial. So no 5 to the power 5 plus 5 plus 5 is 25. You are going to have 25 vertex, 25 edges. So like this. But if I have to pick a teacher to a particular classroom, so like this it will be. If I have chosen this edge A and T1, so now I am not eligible to choose the edges which are having one endpoint as A. Also, I shouldn't choose the edges which are having one endpoint as T1, because this teacher 1 is occupied to classroom A. So these two are blocked. So I have to go and pick the other edges. So maybe D T2 and C T3 and B T4 and E T5. So this is a matching. This is how we match. So out of all the possible cases, this is one particular kind of matching where a teacher is associated to a particular classroom. So this is the usage of this matching. And you see, if your graph has odd number of vertices, then definitely in your matching set, you will always leave one vertex out, because each edge will take out two vertices. If you have odd number of vertices in your graph, then definitely one vertex will be remain. If you have even number of vertices in your graph, then there is a possibility that a perfect matching can happen. Perfect matching means if all the vertices are covered. So you see, if there is no E at all in this particular graph. Okay, so this is how the graph is, let's say. So if you see, by taking this matching, considering this matching, all the vertices are covered. So A, B, C, D, F, G. Every vertex is covered in my matching. So this particular matching is called as perfect matching. So perfect means you are covering all the vertices. So for odd number of vertices in your graph, there is no possibility of having a perfect matching. But for even number of vertices, there might be a chance of having perfect matching. Okay. Any doubts in matching?
The same way we will calculate the independent maximum number of independent set, right?
No, not particularly. Maximum independent set is like, yeah. So here we are referring to edges. Maximum independent set means you have to pick the maximum number of vertices such that no two have a common edge. No two vertices have a common edge.
Okay.
Okay. Yeah. So you replace edge with vertex and vertex with edge here. So no two vertices that are picked have a common edge. So that will be the maximum independent set.
Okay.
Okay, just try look into it. Okay, this is fine. we do the matching of a particular graph? Yes, no,
Yes.
sleeping, boring.
Yes. Yes.
Yes, understood.
Okay. So shall we move forward?
Yes.
Yes.
Sure.
Okay. Okay. Let's move. And now let us look at directed acyclic graphs. So what do we mean by directed acyclic graphs? So directed acyclic graphs means a directed graph with no cycles is called directed acyclic graph. Simply DAG. We call it as a DAG. Directed acyclic graphs. In short, we call it as DAG. So this is very simple. So a graph which is directed, as well as in that particular graph, if you don't have any cycles, so cycles, just recall, we just explain what is cycle, what are cycles means. So if there are no cycles inside my directed graph, then that particular directed graph is called directed acyclic graph, in short DAGs. So I'll give you two graphs now. So tell me which one is a DAG and which one is not. Okay. Now these are the two graphs given to you now. So which graph is directed acyclic graph and
First,
which graph is not
graph.
directed
Understood.
acyclic graph?
Directly.
Right.
First one is
First graph.
direct.
First
Yes.
graph.
First graph is directed acyclic graph. This is a DAG. Yes. And why this is not DAG?
Because from A we can travel to E,
Yeah.
then D, then A again.
Then come back to A, and this will form a cycle. Similarly, I have one more cycle, E to D, D to C, and C to E. So even if you get one cycle, then that is not an acyclic graph. Okay. So therefore it is not DAG. So if it is not acyclic, it is not even DAG. So you can rule it out. So DAGs means directed as well as acyclic. Acyclic means there should not be any cycles inside your graph. And there are few facts about this DAGs. Facts or properties of DAGs you can also call. So facts about these DAGs. So first fact is, so every DAG has a vertex with in degree 0. Okay. So I skipped degree part, right? So let me discuss degree also in short before this itself. Let me discuss degree thing first. and then we will go to that. So degree of a vertex. So degree is also very easy term, but the terminology you should understand. So degree of a vertex meaning, so a vertex, sorry, so the number of edges that are incident to a vertex U is called the degree of U in an undirected graph. So degree of a vertex means, so degree refers to a vertex, okay? In a graph, degree, when I say degree, it always represents regarding a vertex. So saying about a vertex, talking about a vertex. So what that degree means is the number of edges that are connected or incident to that particular vertex. So how many number of edges that are connected to that particular vertex U is called the degree of vertex U in an undirected graph. This you have to note. So degree I will talk only for an undirected graph, and I will say for a directed graph what we will call. So for example, let me take a small example. Okay, so this is a graph with 4 vertices. Now if I wanted to talk about the degree of vertex A, so degree of vertex A in this particular graph will be 2, because this particular vertex A is incident to this edge and this edge. So the number of edges that are incident to vertex A are 2. So therefore the degree of vertex A will be 2. So what will be the degree of vertex C?
C3.
2
2.
or 3?
It's 2. 2.
2. 2. So you just have to look at number of edges that are incident to vertex C. 2. What will be the degree of vertex B?
3.
C3.
3. So 3 edges are incident to vertex B. So 3. And D?
1.
1. Simply 1. So degree of a vertex is very simple. You just have to count the number of edges that are incident to a particular vertex. So that will be the degree of that particular vertex in an undirected graph. So undirected graph, degree. So degree comes only in the case of undirected graphs. And what about directed graphs? What should I call? So in a directed graph, so in the case of directed graph, we have two things now, not degree. So in undirected graph, we have only one number associated to a vertex. But in directed graph, in the case of directed graphs, we have two numbers associated to a vertex. One is called in degree and another one is called out degree. So in a directed graph, each vertex will have in degree separately, out degree separately. And what is this in degree and out degree is? It depends on the edges. Again, so in degree is the number of edges. So in degree, let me write here, in degree of a vertex, meaning the number of edges, directed edges, the number of directed edges that are coming towards the vertex u is the in-degree of u. Okay, so the number of directed edges that are coming towards vertex u is the in-degree, and similarly out degree means out degree of a vertex means the number of directed edges that are going away from vertex u is the out degree. Out degree of u. So now in directed graphs case, we have two numbers. So each vertex will have two different numbers. So one is called in degree and another one is called out degree. And in degree means the number of directed edges that are coming towards the vertex u. So you have to count how many number of edges that are coming towards you. So that will be the in degree. And out degree means the number of vertices that are going away from vertex u. So let me give you example and we will try to compute the in degrees and out degrees. So A, B, C, D, E, and F. Okay. Okay. Let me give directions to this. Okay. So this is a directed graph we have now. So I will compute for two vertices. Then onwards you should answer. So now in degree I will represent with black. So in degree is black and out degree I will give with red. Okay. So the in degree of vertex A will be the number of edges that are coming towards A. So I have to look for edges that are coming towards A. So there is only one edge that is coming towards A. So the in degree of A will be 1. And the out degree of A will be the number of edges that are going away from A. So this is going away from A, from A, from A. So these three edges are going from A to the other vertices. So the out degree of A will be 3. So in degree is 1, out degree is 3. Similarly, I will compute for B. So the in degree of B is, I have to look for how many edges that are coming towards B. So there is only one edge coming towards B. So the in degree of B will be 1. And the out degree will be number of edges that are going away from B. So one edge is going from B. So again 1. So now what will be the in degree of D? Vertex D.
3.
3.
3. So 3 edges are coming towards D. So 3. And what will be the out degree of D?
1.
1. So only one edge is going away from D. Similarly, out degree of E?
2.
Out degree 2.
2.
Out
2
degree
edges
2.
are, yeah, out degree 2. Out degree of F?
1.
1.
1. Only one edge. Out degree of C?
2.
2.
2 edges. So similarly, in degrees of E? In degree of E?
1.
1. F?
2.
F2.
And C?
2.
2.
A
2. So this and this. Okay. So black numbers are in degrees and red numbers are out degrees. So once you compute this in degrees and out degrees also, you can identify whether this is a DAG or not. So if you see, no vertex in this particular graph has 0 in degree. So that means there is a cycle. There is definitely a cycle inside this graph. Okay. So what is, can you give me the cycle? One cycle.
A B C D E and A.
Yeah. So A, B, C, D, E, A is one cycle, or simply this is a cycle. A, D is also a cycle. So this is not a DAG. So in order to be a DAG, the first property of DAG is, if that is a DAG, then definitely there will be a vertex which has in degree 0. So this black number, for one particular vertex, it will be 0. So that is a fact, that is a property of DAG. Okay. So this is the in degrees and out degrees. Remember this, and we will talk more about this in DAGs. So the first fact is, every DAG has a vertex with in degree 0. Let's come back to DAGs. So the next property is the same. Every DAG has a vertex with out degree 0. So these are different vertices. So there will be a vertex which has in degree 0, some other vertex u. There will be vertex which is v with out degree 0. That means there will be a starting point and there will be an ending point for a DAG. And the third fact is pretty well known fact. They do not contain cycles. DAGs do not contain cycles. And fourth one is, these are just the applications. So this topological sorting and longest path. So these two are applications of DAGs. So I will quickly discuss what are these topological sortings and longest path is, and we will move forward. Okay.
A quick question.
Mm-hmm.
A directed acyclic graph can have an edge which is not directed, right? It can have a bidirectional edge also.
If it has a bidirectional, then there will be a cycle, right?
Right. Yeah.
So that will not be a DAG anymore.
Okay. Okay.
You understand,
So
right?
in
Bidirectional
between-
means I can go from that U to V, and I can travel back to from V to U.
Okay.
Right? I can come back to U again.
Okay.
So that will form a two edge cycle.
Correct.
So that will not be
Now,
a DAG anymore.
now in degree and out degree is computed only for acyclic graph, or an ordinary directed graph also in degrees computed.
See, right now we just computed, right? Before itself we have computed the in degrees and out degrees for a normal directed graph. This is not a DAG.
Yeah, but this does not have a bidirectional edge. It has your example has only unidirectional edge. If there were a bidirectional edge, then
so bidirectional edge is nothing but, so you can see it like this. So if it is bidirectional means like this.
Okay.
So it's like you can go from E to A and A to E also. So it's like that edge is like it is going away from E as well as it is coming towards E. So you have to count it twice.
Yeah, it will contribute both to the in degree and out degree.
It will count for both in degree, and now the in degree will change. In degree of E will be 2.
Yes.
Okay.
Yes.
Like
But in a acyclic graph, that bidirectional concept is not possible at all. So we can ignore that and say,
correct.
okay, it's a direct graph which has no bidirectional edges, one vertex in degree 0, one vertex out degree 0, and does not contain cycles.
Only in DAGs, directed acyclic also. It should be acyclic also.
Okay, okay, got it. Sorry to disturb. I just want.
Fine. See, doubts. I accept doubts. Okay. If you are not asking doubts, I feel like you are sleeping, or you are understanding it in a very good way. So these two can happen. So you can. I always accept doubts. Okay. Don't. You can ask doubts. So that is why this session is. So whatever doubts you have, you can ask. Whatever I teach, you can learn. So if I am missing something, you can also add. Fine.
Thank you.
Yeah.
Thank you.
Yeah. So let us take a small example and let me show you in very quickly what is this topological sorting means and what is this longest path. So this, let me take the above example. This DAG. Let us take this DAG only. So this is a DAG. Let us verify our facts first of all. So let us try to. So now in degree I will denote it with blue. Blue in degree. And again same red as out degree. So let us check whether our facts are correct or not by computing in degrees and out degrees. So correct me if I am going wrong, or else you can also say. So the in degree of A will be 0. In degree of E will be 1. In degree of B will be 2. In degree of D will be 4. In degree of C will be 1. Am I correct?
Yeah, right.
Right? Yeah. So now let us do the out degree part. So out degree of A is 4. Out degree of E is 1. Out degree of B is 1. Out degree of C is 2. And out degree of D is 0.
0.
Correct?
Right.
Right? Yeah. Now let's verify our facts clearly. So first fact says there will be one vertex with in degree 0. Is there a vertex with in degree 0?
Yes.
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 Which vertex is this?
A.
A. So there is a vertex which has in degree 0. Is there a vertex which has out degree 0?
Mm.
Yes.
Yes. So vertex
Yes.
D has out degree 0. Yes. So two facts are okay. So again, third fact we already checked. There are no cycles. And the fourth is like we can do a topological sorting. What is this topological sorting is? We are going to arrange the vertices in an order. So in an order means we will start via the paths of the edges. So now look at carefully. What we will do is in the topological sorting, so
Maybe we
treat
should
these
start
edges
from.
are
Maybe we should start from where the in degree is 0, right?
correct, right. So treat this while you do this topological sorting, treat the edges represents the superiority. Okay. So A, E. So there is an edge from A to E. So treat as E is superior to A. Okay. So that means in order to reach E, you have to first reach A, then you can reach to E. It's like an ordering, you can say, or the course building, you can say. So if you have to do course E, you should complete course A first. Okay, unless you complete course A, which is the prerequisite, you cannot move to E. Or you can treat it as tasks. So you have to build a. So there is in the lecture itself, I guess you are building an some hotel. Okay. So in order to build that, you cannot directly what you say, you cannot directly paint the walls before even building the walls. So there will be some task priorities. So first task, what you need to do, you need to collect all the sand, cement, the iron rails, everything. Then you have to build the basement. Then you have to construct the building. Then you have to paint the walls. So then you can start opening the portal. So this will be the task priorities. So like this, treat it like that. So now what we have to do is, this is the sorting thing. Topological sorting means we are keeping the vertices in the superiority order. So the last vertex is the highest superior, or the last task need to be performed. So the first vertex is like the first task. So the first task is like A. So A is independent of, there is no prerequisite to A. So you can start from A. Right? There is no edge that is coming to A, towards A. So that means you can start from A. So you have to do A first. So once you do A, so this is how you have to do topological sorting. Once you do add A in your topological sorting, what you have to do is, you have to remove A and the corresponding edges that are incident to A. So remove it, remove, and remove. Good part is, once you remove the in degree vertex which has 0 in degree, the resulting graph will also be a DAG. So this is an interesting fact on DAG. So you can observe. So I have removed and I have to update the in degrees now. So you see now the in degrees will change. So in degree of E will change to 0. Okay. And in degree of B will also change to 1. In degree of C will also change to 0. And in degree of D will also change to 3. So observe, what you have to do is, you have to pick the vertex which has in degree 0 and add it to the topological sort. And you remove that vertex and the corresponding edges from the from the graph, and look the resulting graph. Now the resulting graph has 2 vertices which has in degree 0 and out degree also 0 we have. So this is a DAG. You can check again. So the resulting graph will be DAG. Now what you have to do is, you can add any one of it. Either you add E or C. So let me add C. So I also follow the alphabetical ordering here. If you didn't follow also, it's fine. You can add E to the topological sorting, but I am adding C. So once I add C, what I have to do, I have to remove this C as well as the corresponding edges, and then update the in degrees of the remaining vertices. So if I have to update the in degree of B, it will be 0, and D in degree will be 2, E in degree will be 0 as it is. Again I got a DAG, but here also again I have 2 vertices which have in degree 0. So I can add any one of the edge. So let me add B. As I am following alphabetical order, let me add B. So once I add B, I will remove B and the corresponding edge, and then update the in degrees. So this is how it will be. Now again this is the DAG, and I have to remove the vertex which has in degree 0 and add it to the topological sort. So A, C, B, E, and remove E. Finally you are left with vertex D which has in degree 0 as well as out degree 0. So add this D finally. Okay. If you observe, we started from here. We started from here. So you see, I have given the topological sorting to be A, C, B, E, D. So if you had treated like these are the tasks A, B, C, D, E, you have set of 5 tasks need to be done, and you can only, the edges represents if there is an edge between from A to E, that means task A need to be performed before task E. So that is how the edges are representing. Then you can perform in this order. Tasks need to be performed in this particular order. You have to perform A first, then C, then B, then E, then D. Also, you have one more topological sorting: A, E, C, B, D, or else you might have this order also: A, C, E, B, D. So like this, there might be multiple topological sortings, but if you pick any of the topological sorting, you see the order, the superior task will be at the right end and the primary task will be at the first. So we will sort it in order. So sorting means ordering. So we are going to order the vertices starting from least to the highest, least priority to the highest priority. Okay, this is what topological sorting means. And also the longest path means we will try to find the longest path in the graph, not the shortest path, longest path in the graph. So longest path in this particular graph will be AC, CB, BD. So like this. So this will also require some applications. You just go back and see how we can compute the longest paths. So there is some algorithm to this. So if I start now, it will take a lot of time. So I don't want to get into that. If you have time, just go back, watch the lecture. Longest, how we can compute the longest path. It is also very easy algorithm only. Like this only it will also be. So you can understand it easily. The main sense of that longest path means in this particular graph, what will be the longest path? So longest path means more number of edges are there in that particular path. So in this particular graph, A to C and C to B and B to D will be the longest path. Longest path have only 3 edges. The longest path in this particular graph is 3 in terms of number of edges. So you can check every other path will be less than 3 only. So from A to B, B to D is of length 2, A to D is of length 1, A to E, E to D is of length 2, A to C, C to D is also of length 2. So like this, you can only have at most 2 length paths, but only this particular path will have 3 length of 3. So this will be the longest path. So how to compute this longest path has some series of steps. You have to initialize first, then you have to start the process. So it's like an algorithm. So it's also have a series of steps involved to find this longest path. Just go through that particular lecture and you will understand it easily. Okay, so this is all about week 10 graph theory. So this is basic graph theory. So main thing is like you just have to understand the terminologies clearly. So the programming students can leave now and prepare for the exam. So if there are any doubts, you can always discuss via mails, I guess. So you mail us, we will reply it. And definitely you just have to keep this in mind that whatever we discussed today, so please go through this first and then go through the other topics. And all the very best and thank you. You can leave. So programming students can leave from here. Now let's jump to week 11. Okay. So week 11 is for only data science students. So any doubts, programming students, any doubts till now?
Quick question.
Yeah.
Will the longest path be connected to topology sorting somehow?
Using this topological sorting only, we will find that longest path.
Oh, okay.
Using this in degrees, and there will be some other number associated to each of the vertex, which is called longest path. So we will
Oh, okay.
update that longest path also. While we update in degrees, we will also update the longest path also. Okay.
Understood. Understood.
Okay. Yeah. Any other questions?
The BFS and DFS concept is not for programming.
Yeah. BFS and DFS is also there. Okay. So let me give you, they are just the algorithms, breadth first search and depth first search. So I will discuss that in short. So BFS is like, it's like exploring the graph. So in order to explore the graph means traversing all the vertices as well as the edges. So while we traverse and we will analyze the graph, explore the graph basically. And this BFS and DFS both does the exploring thing only, exploring the graph thing only. But both are different methods. That's it. So BFS is called as breadth first search, where BFS more focus on and it explores level by level. So it explores the graph level by level. So what does this level by level mean is, we will start with a vertex. Okay, so we will start with one, it is called root vertex, node vertex. So starting vertex, some will call starting vertex also. So we'll start with that vertex and we will start exploring that vertex, and by looking the adjacent incident edges as well as the vertices which are adjacent to that particular starting vertex, and we will explore those vertices first and then we will move to the next level. So let me explain it by taking an example. So if I have a graph, so I will pick the above graphs, one simple graph maybe. Let us take this graph. So I wanted to explore this particular graph starting from vertex A, and I wanted the BFS tree. We will draw the BFS tree. So how we explored the graph, that is what we are going to draw. So we will start with vertex A. So this is a BFS tree. So I will start with vertex A. So this I will represent it as level 0. Okay. So in the next level, so I am here now. I explored vertex A, and then I will explore the incident edges. So I will travel along the edges and I will see what all vertices are there which are neighbors to vertex A. So C, B, D are the neighbors of vertex A. So I will explore them in the next level. So I will explore D, I will explore B. So I will explore C by traveling along AC edge. I will explore B by traveling along AB edge, and I will explore D by traveling along AD edge. So it's like I am at A, I explored A, and the neighbors of A are B, C, D. So I have to explore B, C, D also. So that will come in the level 1. So these will be in the level 1. Okay. So now after exploring, I will visit those vertices one by one. So after exploring this CDB, so I will visit now. So I can visit C, I can visit B, I can visit D also. So what I will do is we will go by alphabetical order. So I will reach B now. So I will visit B. So once I visit B, so this is explored, this is explored, this is explored, but yet not visited. So X marked means explored, visited means this symbol. Treat it like that. Okay, now we have visited B. We are at B. And we wanted to explore graph staying at B. So I will look at what all the edges that are incident to B and who are the neighbors of B and how many of them are explored and how many of them are unexplored. So if I look all these things, B has some 5 edges and some 5 neighbors A, C, D, E, F. Out of those 5 neighbors, 3 neighbors are explored and 2 neighbors are unexplored. So what I will do is I will explore them in the level 2. So from B to F, via this edge I will explore F, and from B to E I will explore E. Okay, so now F is also explored, E is also explored. Now I will go back to A again and I will visit A again. Now from A, so there are still 2 more vertices to be visited. So now that is C and D, and alphabetical order I have to visit C. Now I will visit C. Once after visiting C, again I will explore the graph by staying at C. So I will look how many edges that are incident to C and who are all the neighbors. Okay, B is also explored. So from C, A is explored. So there are 3 neighbors to C, out of which 2 neighbors are already explored and 1 neighbor G is unexplored. So I will add G in the level 2. So again, now G is explored. So I am done exploring at C, but still from A there is one more vertex which is D need to be explored. I will go to vertex A again and again visit vertex D. So once I visit vertex D, I will see the neighbors, but all the neighbors are already explored. So I will not worry about. There is no unexplored vertex left. So I will go back to A and I will go back to B and then I will visit F. So even I visit F. So if you see the graph itself, all the vertices are explored anyway. So the graph is explored. So also if you see the BFS tree, you got all your vertices in this. Okay. So this will be the BFS tree or BFS exploring I have done. So this is the exploring I have done. So we will do this process till all the vertices are visited. So I will visit. So no. From B I will visit E, alphabetical order. From E again I will go back to B and I will visit F. And from F again I will come back to B and I will go to C, and from C I will go visit G. So finally I have explored and visited all the vertices. Once you are done exploring and visiting all the vertices, you will stop the process and the resulting tree will be the BFS tree. This is how the exploring done. So as I said, alphabetical order. So B, C, D, E, F and G. So I started from A, I explored B, C, D in the level 1. Then I have moved to B, and then from B I have explored E and F, and I came back to A and I have moved to C, and from C I have explored G and I went back and I have reached D, and from D there is no vertex yet to be explored, and I come back to A and again I will go to the level 2 now. So once level 0, level 1 are done, level 2 I will reach. I will go to vertex E. I will look out for any vertices which are unexplored. there are no vertices that are unexplored, I will come back to B and I will visit F and I will see are there any unexplored vertices are there. If there is no unexplored vertex, I will go back to B, I will go back to A, and from A I will go to C, and from C I will reach G. And from G I will see if there are any unexplored vertices are there. If there is no unexplored vertices, I will come back to C, come back to A, go to D. So from D there is no vertex tagged to D, so we are done. So this is how the exploring will be done if it is BFS. So it's like level by level. If you see, this is level 0, and in level 1, if you observe clearly, all the vertices which are one length far from A, they all are there in the level 1. So B, C, D, all the neighbors of A. And all the vertices which are in level 2, they are 2 length far from A. You can see from the graph also. So G is 2 length far from G. So shortest path from A to G is 2. And the shortest path from A to E is also 2. And the shortest path from A to F is also 2. So the level 2 vertices, you will get level 2 vertices. Those vertices are 2 length far from vertex A. So like this, if you have level 3, then that means there is a vertex which is 3 length far from vertex A. But in this graph, there is no such vertex. This is how BFS works. Understood? So BFS is actually exploring the graph. So how we explore is the algorithm. This is how we explore. We will start with the starting vertex and we will explore the vertices level by level. Okay. Yeah. Any doubts?
Can we create any edge between D and G?
Already there is an edge between D and G, right?
Okay. We need to go from D to A to C, right? In this way.
D to A.
Edge between D and G.
Okay, in BFS tree you are talking.
Yeah.
Yes.
So BFS, see in BFS tree you no need to have D to G. G is already explored, right?
Yeah.
So no need to again explore G. So yeah, you will explore only once. You won't explore twice or thrice. So while you have visited C, then you have explored already G. Okay, you no need to explore it again. And as this is a tree, you should understand the properties of trees. So tree is the minimally connected graph. Minimally connected means there is no cycles inside this tree. Or if I add one more edge to this graph, to this BFS tree, then there will be a cycle. So you can try. You can add any edge that will create a cycle. So trees are minimally connected acyclic graphs. So that means if you add one more edge, that will create a cycle and that will not be a tree anymore. So exploring means understand the difference between exploring and visiting. We need to explore the graph, that's it. Okay, by visiting few vertices or all the vertices. So while I visit C, I have already explored G and that G will come in the level 2. Okay. Yeah. And if you see in your BFS tree, few original graph edges might be missing like DG and EG, EF. So you see these edges will be missed. This DE, DG, DB, I suppose BC. So these edges are missing. Mostly you don't require those edges to explore the graph. Okay, so you can explore like this. So you start from A, you can explore B, C, D. So if you go to B, you can explore E and F, and if you go to C, you can explore G. Finish. Done. This is how you can explore the graph. Cool.
Yeah, perfect.
Okay. And there is one more thing called depth first search. So we will go in deep first, and we will search, and we will come back. Right now we have done it level by level, and the next depth first search will be done as branch by branch. Branch by branch, I will just show you. For the same graph, I will take with the same starting vertex only. So what I will do is, so it's like an maze. So if you know maze, if you are trying to solve mouse mazes or something, so you have to reach from one starting point to the one end point, and there will be some lefts, rights, and downs and ups you have to turn. So what we will do in general, we will randomly start, and we will go as long as we can go. And if you reach a dead end point, you will come back to the nearest other turning point, and we will move forward. So the same DFS also does the same thing. So this is how it will be. This is how it explores. So we start from A. So you start from A. And previously what we did, we explored all the neighbors. But right now we are not exploring anything. So from A, you will directly go any one of the neighbors. You will directly visit. So you will directly explore and you will directly visit at the same time. So I will go to B. So alphabetical order. So from B, so I will directly go to C. So I won't come back to A again. So from B, I will directly go to C. And from C, so I have already explored A, I will directly go to G. So like this I will explore G. From G, I will go to D. Right? And from D, I will go to E. And from E, I will go to F. Done. Graph is explored. This is how the DFS tree will look. So it's like depth. So we will go in deep. So by picking one branch, we will go to the corresponding to the next vertex, next neighbor vertices. So until we reach a dead end point. So in this particular graph, we didn't reach the dead end point. I will show you one example where we might reach dead end points. Maybe I will remove this, and I will remove this as well, this as well. So A, B, C coming back, D, E, F coming back. Yeah, cool. So if the graph is like this, so alphabetical order, we said alphabetical order, okay. So if you are exploring, so once if a vertex is explored, you no longer have to explore it again. Supposed to explore it again. So I start from A. So from A, I will reach to B. So it's like greedy algorithm. So it's more of like greedy algorithm. So you just go to B. You just try to explore B and visit B. So from B, you will visit C. And once you reach C, it's like a dead end point. You can't go to anywhere. So what you do is you come to the nearest junction point. So what I do is I will from C, I will come back to B again. So B is the nearest junction point, previous junction point. So from B till I can go to E, F and D and A again, but A is explored, C is explored. So I have to pick the next alphabetical order. So I will go to D. So from B, I will go to D. And from D, I will go to the next alphabetical unexplored alphabet vertex. So I will go to E. So from D I will go to E, and from E I will go to F. See, once I reach F, I have no longer unexplored vertices that are adjacent to F. So I will come back to E. Next nearest junction I have to come. So same backwards. So I have gone from E to F. So I will come from F to E again, E to D again, which is the nearest junction again. So from D, there is one more unexplored vertex G. So that I will explore. So like this, I will go in deep. Once I reach the dead end point, I will come to the previously got junction point, previously having junction point, and from there I will again explore it. So it's like going too forward, reaching dead end point, coming little backward, and again going forward. So like this. This is how DFS does, and BFS does level by level. Okay, and these are called branches. So this is one branch. So this is one branch. This A, B, D, F. This is the longest branch in the graph, and this is the third branch. So there are 3 branches in the graph, and if you observe correctly, between 2 different branch vertices in your DFS tree, there is no common edge. You can see. So C and D will not share an edge. C and E, there is no edge. C and F, there is no edge. F and G, there will not be edge. So what if there is an edge? What happens? So what if there is an edge between C and D? What might have happened? So what if this edge is there?
Cross stitch.
No. What if this edge is there in the original graph? Once I visit C, I would have visited D in that particular branch itself. While after visiting C, I would have visited D here. But I am having D in the other branch. That means there is no edge between C and D in my original graph. So like this, you can predict the original graph also. Okay. So between 2 branch vertices, there will not be an edge. Definitely there will not be an edge. If there is an edge between C and E, so then once I explore, so if I start from A, I explore B, I explore C. Why I came back to B? Because there are no vertices that are adjacent to C that are unexplored. Then only I will come back, right? If there is an unexplored vertex that is adjacent to C, then that would have come in the same branch only. Right?
Okay.
Right? Yeah. So that is why same branch vertices will not have, different branch vertices will not have a common edge sharing. Okay.
So we can visit like A to B, B to F, F to E, E to D, and D to G, right?
A to
Is that
B.
possible?
Yeah, that
A
is
to B,
possible,
B to F.
but I just said pick the alphabetical order.
No, because it is depth first. So I thought this will be more depth.
See, that is what you can see. If alphabetical order is not mentioned, you are doing the depth first search via alphabetical order or numerical order. If the vertices are labeled with numbers, we just give you just have to do the depth first searching in alphabetical order. So once you reach
A
B,
rule about it.
huh?
So there is a rule we should follow.
Like yeah. So there will be a if there is a rule given to you, then you have to follow that rule. If it is not given, so then you can pick whichever vertex you can explore. You can after A, you can pick D, or you can pick B, or you can pick D also. So you can directly go to D, right? A, D, C, F, B, C. So you can explore the graph like that also. Okay. So there will be multiple DFS might be possible. That is why we give ordering to it. So you just have to go alphabetical ordering or numerical ordering, like. Okay. And also this DFS tree will change with the starting points. So here the root vertex I have taken it as A. The starting vertex I have taken it as A. So you may not get the same graph if I start from E. So you might be getting some different DFS graph. Same works with BFS also. So it depends on my starting point as well as the order in which I explore the vertices. Am I following any particular order while I explore? Hmm?
More or less. Understand.
Yeah. Okay. Okay, then. Yeah, those are the main topics in week 10. So again, these are not the only topics we have within the given short time. These are the topics I am able to cover, and these are, compared to others, these are most important. Okay. So let's move to week 11. I will deal with the
Another
Dijkstra.
doubt.
Yeah.
I'm a programming student, so the graphs of polynomial is important for me. Like consider it
Yeah,
as
yeah. They are important for you. So only
because that
calculus
is
part
not
you
in
don't have.
the playlist.
Hmm?
Because that is not in the playlist. It is I have to see it through data science playlist. For the degree of programming playlist, it is not there.
Oh, graphing of polynomials. Week 4 you are referring to, right?
Yeah, exactly.
Okay, let me check with that. Most probably you don't have the applications of graph theory, which is week 11, algorithms, and you don't have that calculus part, week 7, 8, 9. Apart from these two, I think you are going to have. Let me check with the team. Okay. Okay. So we will add that playlist to programming also.
You will update it. That
Yeah, we will upload. We will.
thing.
Or by now, see, it's already Wednesday. You have 3 or 4 days, right?
Yeah, that's
Yeah.
yes.
So maybe you just, for now, you just go to the data science playlist and watch the videos. Maybe by tomorrow we will try to add the videos. Okay.
Okay.
Yeah. So yeah, I will quickly finish week 11 also. Week 11 we don't have much things to discuss. Very few, two or three topics, and that also very easy topics. That to algorithms only. So I will discuss this Dijkstra algorithm. So Dijkstra algorithms. Algorithms, I prefer taking an example and explaining the things. It will be much more clearer to you. So let me take an example. Oh, okay. Before this, for this we need weighted graphs also. So let me deal. What is the weighted graph means is. So weighted. Let me explain weighted graphs first. Okay. Weighted graphs is in a graph. In which each edge is associated with a number. The number, or we say weight. Okay. So right till now, whatever you have seen, each and every edge carries equal weight. So we didn't mention any number to each and every edge. But right now, weighted graphs means each and every edge will be associated with a number or weight, and that kind of graphs are called, this graph is called weighted graph. Okay. So let me give you how we can find the shortest paths in a weighted graph. So that is what we are going to do in the Dijkstra's algorithm. So basically Dijkstra algorithm says, okay, this is how the example will be. If an example I need to provide C, D and E. So I will give weights to each of the edge, 2, 3, maybe some 1, some 7. So now you see this 2 represents the weight of this edge. So this edge carries weight 2. This edge carries weight 3, which is more than the previous edge. And this edge carries the highest weight, which is 7. So in particular, these weighted graphs are now very much useful in real life also. You can treat it
Tolls.
like
Tolls, amount of toll to be paid.
amount of toll or distance you have to travel from one city to another city, shortest distance, or the amount you have to spend to reach from point A to point B is some 2 lakhs. It's like 3 lakhs, 7 lakhs and 1 lakh. So in order to reach D, how short? So what is the shortest amount I have to, so minimum amount I have to pay. So maybe paths are like this. So 4. So like this. So if there is like this, I can go to D via A to C and C to D, or I can go from A to B, B to C and C to D. So whichever path I can, whichever path is there, I can choose that. But I have to pick the minimum path. So every individual tries to minimize the spendings and maximize the profits. That is how human brain works, right? So that is what we are going to do now. So what we are going to do now is, in this particular Dijkstra algorithm, we are going to find the shortest path in terms of weights. Okay. So initially, okay, let me give this as some 6. So if no number is associated, okay, if no number is associated, the shortest path from A to D will be, so what will be the shortest path from A to B? A to D. Yeah.
ACD.
ACD. So it requires only 2 edges. So this will be the shortest path from A to D. So this shortest path I refer in terms of number of edges. Okay. So if weights are associated, in the same example, I have associated weights now. ED, and I am assigning 2, 3, 6, 7 and 1. So now what will be the shortest path?
ABCD.
ABCD. So the shortest path from A to D will be A to B, B to C, C to D in terms of path weight. So path weight is actually all the, so in the path you just sum the weights of all the edges. So you see the path, so this is the path and this edge weight is 2, this edge weight is 3 and this edge weight is 7. So the path weight is, the total path weight is, you just add all these things, 2 plus 3 plus 7, which is 12. But if you see, initially we thought A to D, AC, C to D is the shortest, but that will not be the shortest in terms of path weight. So if I look at the path weight of the path, so A to C, it is weight is 6 and C to D weight is 7. So the weight of the path or path weight will be 6 plus 7, which is 13. So this 13 is greater than this 12. So the shortest path from A to D in terms of path weight is A to B, B to C, C to D. So this is the difference. So if there are no weights assigned to the graph, then the shortest path will be in terms of number of edges. But if the weights are assigned, so we will compute the shortest paths in terms of path weights. So sometimes it may be like the shortest path itself be the, so whatever the shortest path you get in terms of number of edges will be the shortest path from will be the shortest path in terms of path weight also. It can also happen, but there might be chances that it may not happen also. So always, it is not always that shortest path in terms of number of edges will be the shortest path in terms of path weight. So you have to remember that also. Okay. So now let us discuss this Dijkstra's algorithm. So this algorithm we will use to find the shortest path from a fixed vertex u to every other vertex in the graph which has non-negative edge weights. So your graph can also contain negative edge weights also. Sometimes it is not always that you will have positive weights. So sometimes the weights can be -1 like this. Okay, it can also have negative, but if it has negative weights, we cannot use this Dijkstra algorithm. So if I have to perform Dijkstra algorithm to find the shortest path from one fixed vertex to every other vertex, then my graph should not contain any negative edge weights. So it should always have non-negative edge weights. It can have 0 also, but negative is not allowed in the Dijkstra algorithm. And what we are trying to do, we are trying to find the shortest path from a fixed vertex. So now the source vertex, we call it as source vertex or starting vertex. We are going to fix that vertex, and we are going to find the shortest paths in terms of path weights, edge weights, in terms of edge weights to every other vertex. So I will take an example and we will try to find the shortest path from a fixed vertex to every other vertex. So let me take it like this: A, B, C, D, E, F. Okay, and also I will assign some weights to this, to 1, 1, 4, 5, 3, 4, 6, 1 and so 2 and 1. No, 1 and 2. Okay, so I have also assigned weights to each of the edges. Now I am interested to find the shortest paths to every other vertex from vertex A. So this is my source vertex. I will call this as source vertex. So this vertex is fixed now. So I have fixed this vertex, and this is how the algorithm goes. Okay. So we are going to initialize some numbers to every vertex. So how I will initialize this is the initialization I am doing. So I will initialize 0 to vertex A because that is the starting source vertex, and infinity to every other vertex first of all. So infinite, 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 and infinite. Okay, so this is the initialization. So for every algorithm there will be so what I initialize So let us call this as distance value. Okay. So distance value of A is equals to 0 and distance value of vertex I to be infinite, where I is B, C, D, E, F. Okay. So this is the initialization I have done. So now what I will do is I will update the distance values of edges and vertices of the vertex A. So updating means how I will update is, so I will take the edge weights into the consideration. Now I will see the edge weights. So the edge weight of AB is 2. So I will either I will take the minimum of infinity and 2. Minimum of infinite and 2. So I want the shortest path, right? So that is why I will pick the minimum value. So minimum of infinite and 2 will be 2. So I will update it. So I will update the distance value of B to be equal to 2. And I will update, similarly I will update the other adjacent vertex, which is C. So minimum of 1 and infinite, it will be 1. Okay. So in the initial stage, what happened is, first step, what happened is I have updated my adjacent vertices of A. Okay. Now I will move to any one of the adjacent vertices of A. Okay. So where I will move is to the shortest value which has. So I will move to C. No, because it has the distance value minimum. So among B and C, it has the minimum value. So once I move to C, again I will repeat the same process. So I will look at the adjacent vertices of C and I will update the distance values of the adjacent vertices to the minimum values. So now once I reach this C, there are 3 adjacent vertices to C: B, D and E. So B, if I consider B, this edge BC, the edge BC weight is 1. So I will add, so 1 plus 1, it will give me 2. Already the value is 2. So minimum of 2 comma 2 will be 2 itself. So it will not update. So it will remain 2 as it is. So it will not update. So the weight of B, or the distance value of B, will be distance value of C plus the weight of BC. So you have to update like this: minimum of distance value of C plus edge weight of BC, or already having distance value of B. So this, if you compute, you are going to get 2. This, it is already 2. So minimum of these 2 will be 2 itself. So this is 2. Okay. So I will go to the next adjacent vertex of C. So D and E. So again for D, so minimum of distance value of C plus the weight of CD. So it will be 1 plus 3, which is 4. 4 comma, already the distance value of D is initialized to infinite. So minimum of 4 comma infinite will be 4. And here also, if I update, I will get 1 plus 6, which is 7. Okay. So now what I will do is I will move to the next adjacent vertex of A. So once I am done with C, I will move to B. So after moving to B, I will repeat the process. So I will look for the neighbors of B. So these 3. So B, D, E, C. So we have D, E, C. So you don't need to check C again, because BC weight, so BC edge weight is already checked, so it will not alter much. So we have to check via this edge and this edge. Via this edge, the distance value of D will be distance value of B plus the weight of BD. So that will be 2 plus 4, 2 plus 4, which will be 6. So you have to consider minimum of 6 comma initially, so not initially, before we have the value as 4. Right now with this edge, we are getting the minimum shortest path as 6. So we have to pick the minimum shortest path. So minimum will be 4. 6 comma 4, minimum of 6 comma 4 will be 4. So it is not updated. So it will remain 4 itself. But if you see on the other side, via this edge, so the distance value of B is 2 plus the weight of edge BE is 4. So the distance value of E will be minimum of 2 plus 4 comma 7. 2 plus 4 is 6. So I have to pick the minimum of 7 comma 6. So the minimum will be 6. So like this, I will update. So I'll update to 6. So now this edge is done, this edge, all these edges are done. So now I will move to the next vertex, next neighbor. So either I will move to E or D. So it's better to move to the minimum value vertex. It's not like mandatory, it's better. So I will move to D. So again, this edge is already came into the consideration. So you don't need to worry about that edge. So you have to worry about this edge and this edge. So if you see this edge, the distance value of E will be minimum of 4 plus 5 comma 6. So the minimum will be 6 as it is. So we don't worry about this 9. So it will not update, it will remain 6 as it is. But if you see here, the distance value of F is at infinite. Along with this edge, the distance value of F will be distance value of D plus this edge weight. So it will be 5. So minimum of 5 comma infinite will be 5. So this will get updated. And finally, I have to consider this weight. So if I consider this weight into the consideration, so the distance value of E is already 6. I also have a weight which has 2. So the path weight will be 6 plus 2, which is 8. So I will not update. So 5 comma minimum of 5 comma 8 is 5 only. So finally, once you are done with all the edges, you look the final values, final red values. So whatever the values you are going to have, those are the values or those are the shortest paths in terms of edge weights. You can check. So in order to reach C, the shortest path is this, A to C from A. So these are the shortest paths from the fixed vertex A to every other vertex. Okay. So from A, if I have to reach C, it is enough to travel via this edge and the weight of that edge is 1. And in order to reach B, I can travel along this edge or this edge. Both are the shortest paths here. So AB, direct edge AB is the shortest path to B, and also A to C and C to B is also the shortest path to B. So we have two shortest paths. And for D, you check for D. So this A to C and C to D. So this is the shortest path. Okay. So this is the shortest path in terms of edge weights. So even you have shortest path with two edges, A to B and B to D, but that is not the shortest path in terms of edge weight. So that edge weight will be 2 plus 4, which is 6. So that is not the shortest. So A to C, C to D is the shortest. So like this 6 is also A to B, B to E. So this is the shortest path to E. And this 5 is this A to C, C to D, and D to F. So this is the shortest path if I have to reach from A to F. So there are, out of many possible paths from A to F, this will be the shortest path in terms of edge weights. So A to C, C to D, D to F is the shortest path in terms of edge weight or path weight. Okay. Any doubts? Any doubts?
The question will be from a given vertex to another vertex, which is the shortest path. Is that the type of question? Or
Yeah,
it will...
that is how it will be. Like see, the same thing. So the nodes represents maybe the cities, and these are the flight costs, the direct flight costs. We might ask you like what will be the short minimum amount I have to pay in order to reach from Delhi to Mumbai, or something like Hyderabad to Kolkata, like this. So this is how the questions will be. So what you have to do is, so you have to start from Kolkata and you have to find the shortest path to maybe Delhi. So if you ask the question like from Kolkata to Delhi, so what will be the minimum amount I have to spend? So then you have to look out for the shortest paths in terms of amounts or the weights. Okay, out of all possible paths, you have to find the minimum path.
Yeah.
And the weight of that path also, how much minimum amount I have to pay. So how much minimum, so what is the minimum path weight here from A to F? It is 5. Right, in order to reach E it costs more than in order to reach F. So like this is how it will be, and you can use Dijkstra algorithm in these kind of cases.
Okay.
Yeah, so that is about Dijkstra, and there is one more algorithm called Bellman-Ford. And the difference between Dijkstra and Bellman-Ford is Bellman-Ford you can use it even though you have negative edge weights. So that is also between that is also finding the shortest paths from a fixed source vertex to every other vertex, where you will have negative edge weights also involved, but not negative cycles. So negative cycles meaning if you have any cycle with weight, total weight to be negative value. So something like this. So you have a cycle -2, 1, -1. Okay. So this cycle, the weight of this cycle will be -2 + 1 -1, which is -2. So we will say this is a negative cycle. So if you, in your graph, if you have a negative cycle, what happens is, if I go around this negative cycle, so my weight will get decreased. So for the first time, if I okay, I start from C and I go to A and I go to B and I come back to C. So the path weight will be -2, and from there if I start again, go to A, go to B, come to B and reach C, then my weight will become -4. Like this, if I keep on rotating in this cycle, my weight will get reduced and reduced. So this will not give me the shortest paths, right? Get the sense of this. So if I rotate in this cycle itself, my weight will decrease, keep on decrease. So this is the path I am talking about. C to B, B to A, again, sorry, C to A to B, again B to C, again C to A to B, B to C, C to A, B, C, A. So if I keep on doing this process, if I look at this weight, so -2, 1, -1, minus 2, 1, minus 1, minus 2, 1, minus 1, minus 2. If I look at the weight of this, it will be like 1, 2, 3, 4, minus 8. So you see, minus 2 is not the minimum, minus 8. Again, if I take a loop, I will get minus 10. If I take one more loop, I will get minus 12. So minus 12 is minimum than minus 10. So like this, minus 14, minus 16, minus 18, I can reach till minus infinite also. So we are not going to get the minimum. So algorithm will fail. So that is why we shouldn't contain negative cycles, but negative weights are allowed in Bell-Manford algorithm. Okay. And there is one more algorithm which is Floyd-Warshall algorithm. In that algorithm, we can actually find shortest path from any vertex to any other vertex. So it's like there is no fixed source vertex. So we will try to find from one vertex to any other vertex, we will find the shortest path within a table itself. So these are time taking algorithms, and also it's not that important right now. So as this is the qualifier exam, we are not going to focus more on this kind of algorithms. So you don't need to worry about these algorithms. If you are interested, just go and watch the lectures and try to understand what this means. Okay. And finally, I just wanted to end this with a simple concept which is called spanning trees. And how do we find minimum cost spanning tree? So spanning trees of an undirected graph. So we will, in this particular spanning trees concept, we will only deal with undirected graphs. We are not going to deal with directed graphs. So you don't need to see the directed graphs in the spanning trees. So I will refer it as undirected graph only. So the spanning tree of an undirected graph G, so I will say G is a subgraph that is a tree which includes all the vertices. So understand this. Subgraph meaning, so I will have few edges out of the big graph G. I will remove few edges and make it a tree. So I just said what is tree meaning. Tree is just minimally. So a tree is minimally connected acyclic graph. So what this means is, so this is a tree because you see this is the minimally connected. So if I remove one edge, this will no longer be a connected graph. So there are two components in this. This is one component and there is an isolated vertex. So they are not connected. So there are two different graphs which are not connected now. So it becomes two different isolated, two different graphs kind of thing. So two components we say. So if this is the case, then this graph is called as disconnected graph. So if I remove one vertex from this tree, that will fail the property of connectedness. If I add one more edge, so add any edge, if I add AD edge, this will create a cycle. This will no longer be acyclic. So ACD is a cycle. Or if I add an edge between ED, so ECD will become a cycle. If I add edge between BC, ABC will become a cycle. So like this. So I can't add an edge, it will fail the property of acyclicness. I cannot remove an edge, it will fail the property of connectedness. So trees are minimally connected acyclic graphs. And the number of edges in a tree will be n minus 1. If there are n edges, n vertices, then in your tree there will be n minus 1 edges. You can check. So in this particular graph itself, if there are 5 vertices, there are 4 edges. So because for connectedness, you need at least n minus 1 edges, In order to be acyclic, you need to have at most n minus 1 edges. So at least n minus 1, at most n minus 1 will give us exactly n minus 1 edges. Okay. So this is tree. This is tree. And what we require is, out of big graph, big given graph, undirected graph, we are going to pick the subgraph. So by removing few edges, we are going to get a subgraph that is a tree. Okay, and we shouldn't remove vertices. All the vertices should be there. We should only remove few edges and make the graph as a tree. And that tree, that resulting tree will be the spanning tree. Why we call it spanning tree is because it is spanned from this graph. So spanning means we have developed a tree using this original graph G. So we have spanned the tree using this graph G. So every spanning tree is a tree, but not every tree is a spanning tree. So there might be few trees which are not spanned from any graph. They might be the graphs itself. Okay. To understand the difference, spanning trees are always spanned from some graph, some undirected graph G. And trees are all one type of graphs. So every spanning tree is a tree, but not every tree is a spanning tree. So it is not that every tree is spanned from some other graphs. Okay. Tree is superior to spanning trees. So it's like you can treat it like that. Spanning trees are subset of trees. Spanning trees are subset of trees. Okay. So like this. So this is what a spanning tree, and we are going to find the spanning trees. If a directed graph, undirected graph is given to us, we can find the spanning tree. A simple example will be like this. So I will use numbering now. So I'm fed up with alphabets. So 0, 1, 2, 3, 4. Okay. So like this is a graph, and we can span a tree. So the corresponding spanning tree will be like this. So you can have multiple spanning trees for a given graph. So one spanning tree will be like this. So this is a spanning tree which is spanned from this graph G. Okay. So you can create your own spanning trees. So there might be, you can take it like this. You can actually, so 3, 1, 2, and 2 to 4. So this is a spanning tree. Okay. So there can be many spanning trees for a given graph. And what is this minimum cost spanning tree is? If I have a weighted undirected graph. So I will try to find out of these all possible spanning trees, I will find the spanning tree which has minimum weight. So which has minimum cost. Cost of a spanning tree is nothing but after getting the spanning tree, I will add all the edge weights. So that will be the cost of the spanning tree. And whichever is the minimum, that will be called as minimum cost spanning trees. How we will find the minimum cost spanning tree is, you can use Prim's algorithm or Kruskal's algorithm. We have algorithms, two algorithms. So you can use either one of it. I will show you both within some 10 minutes. So you can pick whichever you like, you can pick that algorithm and learn that algorithm properly. So we will start with Prim's algorithm. Okay. Let me pick a good graph. So right now I am having edge weights, so I will use alphabets again. So if you want. Okay, like this. So let me give this weight is 1, 2, and this weight is 2, 4, 3, 3, 5. Okay, I have to give weights to this also. 2 again and 4. Okay, so I have given weights to, so this is a graph G we have, and now I am interested to find the minimum cost spanning tree using Prim's algorithm. So what Prim's algorithm says is, so you pick the least edge, so least weighted edge. So here we have 3 edges, you pick any one of it, any one of it. So I will develop my algorithm, so my spanning tree like this. So I have picked AF edge. So now what you have to do is, so you have to pick the edge which is adjacent to this edge AF and also having the minimum weight. So this edge with this edge is adjacent, this edge is adjacent, this edge is also adjacent. Out of these 3 edges, if I look at the weights, this weight is 3, this weight is 3, but this weight is 1. So FC weight is 1. So I have to pick the least edge weight which is adjacent to this edge AF. So this C. Okay. Now what I have to pick is, now consider these 2 edges and look in the graph. So whatever the edges that are adjacent to the any one of these edges and also having the least weight. So you see this edge has this and this edges as adjacent, and this edge has this edge has adjacent, and yeah. So among these AB, BC, CD, EF, whichever is the minimum, pick that edge. So among these 4, I have the minimum edge weight as CD. So pick that. So I am building my spanning tree. So now next is, now consider these 3 edges now. So AF, FC, CD. So the edges which are adjacent to at least one of this edge. So you have to consider all the edges, and out of all the edges, whichever is having the minimum edge weight, we are going to pick it. So now, so we'll use one more color. These 3 are already in our spanning tree. So now the edges which are adjacent to these 3 and also having the minimum, and also one more condition we have, we are building a tree. It should not contain cycle. So no cycles are allowed. So these 3. So look at the red colored edges and look at the adjacent vertices. So for this edge we have, okay, this edge is also there. So for this edge, this and this. So these many edges are there. For this edge we have this. So this is already there. So this and this. And for this edge we have this. So like this, there will be many possibilities. Out of all this, pick the least one. So now you see, I can pick AD. So the least vertex is edge is AD, ED, DB. Pick any one of it. So again, we can pick any one of it, but you have to make sure you shouldn't contain cycles. So if I had picked AD, so what happens? We will see. if I had picked AD, so which is having the least weight, next least weight, which is 2. So if you observe, now I have got a cycle. So A, D, C, F, A. So I started from A and I have reached back to A by traveling with some vertices and edges. So that means you shouldn't, this is not a tree anymore. If it is not tree, it will not be a spanning tree. So you have to make sure that
can't we just ignore the edges which has A, F, D, C? In that case, we'll have no.
So, how will you know that which edges are adjacent to those edges?
No, I mean to say, if we pick up a edge and go that way. Got it. Yeah.
So I cannot pick AD because it creates a cycle. So I will try to pick BD or ED. So both works actually, both the things work. So let me pick BD. So which is of weight 2. Okay, now I have 4 edge weights. So 4 edges actually, AF, CF, CD, BD. So all these 4, next I will look into all the edges which are adjacent to at least one of these edge and having minimum weight, and also it should not create cycles. So now I have minimum to be 2 again, ED. So if you see, you will have the minimum to be ED only. So all other weights are greater than 2. And again, if I take AD, it will create a cycle. So there is ED. So I will add ED edge to my spanning tree. So now I have got this. So is every vertex came into my spanning tree? Yes, no.
Yes.
This is a spanning tree. We are developing the spanning tree. So if you see right now, the spanning tree looks like this. So A, F, I have vertex A, B, C, D, E, F. And also you can check. So do I have to check further or not? You have to check by, if this is a spanning tree, this is a tree. So tree should contain n minus 1 edges. So that means you have to add n minus 1 edges. So you have 6 vertices in your graph. That means in my spanning tree, I should have 5 edges. Once you add 5 edges in your spanning tree, then you are done. So that will be the spanning tree. And that will be the minimum cost spanning tree. So the cost of this spanning tree will be 1 plus 1 plus 1 plus 2 plus 2, which is 4 plus 3, 7. Okay. So no other spanning tree will give you less cost than 7. So you can check. So you pick randomly any spanning tree. There are, I guess, more than 10 spanning trees are possible for this particular graph. Out of all the spanning trees, this will give you the minimum cost, which is 7. So all other spanning trees will have more than 7 cost. And the process is like this: pick the least edge weight and then build the spanning tree. So you have to build the spanning tree. So why this works is because,
there be only one tree which has the cost 7, correct?
Which has the
Cost 7.
What is first 7?
The cost 7. COST.
See, sometimes you might get multiple spanning trees also having the same cost.
Oh, okay.
Yeah.
That was my question.
Yeah. So I can give you example right away here only. So if my if this is 2, okay. So this is one spanning tree, and I can draw one more spanning tree. So by taking So instead of this edge, I can pick this edge. And even this spanning tree also has weight 7. Okay. The cost will be minimum. So whatever the number you are going to get, final number, minimum cost of the spanning tree will be unique.
Yes.
Okay. If it is 7, it will be 7. Minimum cost will be 7. You won't get spanning trees which has cost less than 7 at all. You might get duplicate spanning trees which has exactly 7 cost. It might be possible. Okay.
Okay.
But Prims, yeah, Prims actually uses the connectedness of the tree. Okay. So if you understand clearly, so it will build like, so first it will take an edge. Definitely this edge need to be connected to some other edge because this tree is a connected tree. So we will look for the neighbors of this edge and we will build using the property of connectedness. Okay. So Prims uses that. And Kruskal's is a lot more easier easier algorithm, I feel, but some people might argue Prims is easier. So what Kruskal does is, so this is also algorithm to find the minimum cost spanning tree only. But what Kruskal does is, he will arrange all the edge weights in order, in numerical order. So how he will arrange is, so he will take this graph. So let us take this graph itself. So you are no longer choosing the minimum edge weight and developing. Instead, what you are doing is, so we are going to arrange our edge set in numerical order in terms of weights. So we are going to we are going to arrange it in numerical order. So AF, CD, BD, AB, BD, AD, ED, and then comes FE. All these are weights of 1 and these are weights of 2, and the FE is weight of 3, and then we will move to 4, AE and BE. These are weights of 4, and finally BC, and this is the weight of 5. So what he does is, he will arrange all the edges in ascending, in numerical order, so from minimum to maximum. Then what he does is, he will take the first edge. So now he will build the minimum cost spanning tree. He will take the first edge, and next he will move, he will add this edge to the spanning tree, and then he will move to the next edge, so CD. So CD he will add, so there is C, yeah, so D, C, so this is B, there is E. So I am building the spanning tree now. So what he does is, he will add this edge to the spanning tree, and he will check if there are cycles or not. If there is cycle, he will exclude that edge and he will move to the next edge, and he will complete till the end. So AF is the starting edge, so there will not be any cycles at all. So he will add AF, and the next edge also he will add, because with 2 edges we cannot create cycle. So we will add that edge also, and next he will move to BD, next edge is BD. So he will try to add BD. If it creates a cycle, he will exclude BD. If it doesn't create a cycle, he will add that edge. He will add that edge, and edge weight is 1. and next he will move to AB. So AB, so if I add AB, it is not creating any cycle. So he will add that edge. So this edge is also added. So now he will look at why BD came again. What is this? Sorry, FC, right? This is FC. So FC weight is 1. Okay. So here it didn't create cycle. Now he will move to the next edge, which is BD. So he will try to add BD. So if he tries to add BD, that will create a cycle. So therefore, he will exclude BD. So he will not add BD. So he will remove BD, and he will move to the next edge. So he will move to AD. So once he moves to AD, even here also if you see, if he tries to add AD, even this also creates a cycle, AFCD A. So therefore he will exclude AD also. So he will not add, and he will move to the next edge. Then the next edge is ED. So we will try to add edge ED. So adding edge ED doesn't create any cycle. So he will add it.
We can stop here because n-1 is achieved.
You can stop here. So once n-1 is achieved, you can stop here. Or else, even though if you perform till end, FE will create a cycle. He will not add. AE will also create a cycle. BE will also create a cycle. BC will also create a cycle. So you can stop here. So once you get 5 edges, n-1 edges, you can stop, and this will be the spanning tree.
Okay, but here one query, but the minimum cost become 8 here. Okay, so it is coming more.
Why it is 8? This is 1 1.
Okay.
So the minimum cost is 1 plus 1 plus 1, 2 plus 2. I am about to make that note.
Okay.
So note is whatever algorithm you use. So even you use prims or Kruskal's, your minimum cost MCST will be unique in terms of cost.
Okay.
So your minimum cost will be same for both, or you can say same. Your MCST will be same in terms of cost. Instead of unique, will be same, you can say. So if you have used Prim's algorithm, you got minimum cost spanning tree, minimum cost as some 10. Then if you use Kruskal's also, you will get 10. So it's the two different ways of getting the minimum cost spanning trees. That's it. Different algorithms.
Okay. But here the Kruskal looks very easy. We can simply you can make it.
See, even my point also is like, even I feel Kruskal's is easy, but some will argue that, see, it depends on someone's mindset. So some will say Prims is way easier than.
Correct.
The checking of the what do you call the cycle may be difficult for some.
Prims, right? Okay. So so that is what I suggest. So you no need to go through both the algorithms. If you are having time, you just go through both the algorithms in deep. But if you are not that much worried about this concepts to learn just now, right now, then for examination point of view, learn one algorithm perfectly. Okay. So these are the important things you have to keep in mind. And I hope you all will perform best in the exam. And thanks a lot for joining this session. And
thank you very much. We conducted a session for 4 hours.
So it was a long 4-hour session. So I hope this session will helpful to you. Yeah. Can you share this PDF? I will ask them to somehow share it with you guys, and I don't know how they will share. But I will send them to upload somewhere. Okay.
Okay, sure. Thank you.
Yeah. Thanks, guys, and all the very best for your qualifier exam.
Thank you. Thank you.
Yeah. Bye.
Bye.
All the best, everyone.